Episode 8 of Machine Learning at Helmholtz-Zentrum Gestalt. We have a really interesting, exciting paper this week. We have the first author to discuss it with us. This paper, recently, very fresh off the press in Nature Geoscience, discusses how we can fill in missing data when we want to analyze large data sets stretching over big ranges of space or time, but we don't have the observations we need at every time or every place. How can we infer or impute these missing observations from the observations we do have? And this is a topic which has received attention in the literature over decades, but there are some new techniques which are really bearing some very promising fruit using machine learning. And to explain this to us today, in his recent paper and in person on our screen, we have Christopher Caddo from the German Climate Computing Center. Chris, I'm going to turn it from the observations we do.
Great. Thanks, David and Marcel, for putting me here today. I have to say, I really love the seminar. I love to discuss stuff with you. So I'm happy to show you today our paper, which came out recently. I'm not able to do it as cool as David and Marcel, so I have to give you a real presentation on it. But I have the paper next to me. I have the code next to me. So my suggestions would be like, I go through the talk. You can always interrupt me if you have questions, and after also we can discuss stuff afterwards. So I really love the title David gave it, Uncharted History. That's pretty cool. You give a nice introduction to it. I start with the presentation now. So I really want to give a short introduction into the world of image in painting, which is kind of the buzzword here in terms of machine learning techniques. So it's basically restoration. So, and if you have no idea what restoration is, it's kind of if you have paintings of photos and they are maybe old, like we have on the left now with a painting of Jesus, and a photo of a lady on the right side, is there a question? No? Okay. In machine learning and in all these image stuff, we call it ground truth. I put it into quotation marks because basically nothing here is a ground truth. And then usually what comes into play if you have the ground truth is time with paintings and photos. So over time, these things get broken. So you have damaged paintings or damaged images and photos. And it's a pretty old idea that we could like restore the real painting or at least give it kind of the real image back in a way. So I want to start with the left side. So this is a painting from the Sanctuary of Mercy Church in Boya, Spain, and there was a restorator saying, yeah, I could restore the picture, the painting on the left in that church, and for free, she said. And this was what was coming out of it. So that's a pretty famous example. This painting restoration went viral over the world. That was a huge success for the church, actually, because a lot of people wanted to see this new image of Jesus, and it was a huge success story, but you could agree that it's not really close to the original one. And if you go to the right side of the photos, right, so we have the ground truth, the broken image, and then the restoration, which is a lie, because actually the photo I was showing in the beginning on the ground truth is the restoration, because the original photo is not there anymore because it was a real photo. Right, an old photo. And what really strikes me about the restoration on the right side, which was done with deep learning techniques, is probably it's even better than the original one because it learned on modern photographs, and probably it's even better than the original one. And that is kind of, I mean, this is a quite big motivation that there's a lot to gain and a lot to get with these techniques. And I wanted to show you guys this example because there's always a big discussion about artificial intelligence. Are they really intelligent? So I brought this example here to compare human intelligence and artificial intelligence. And you can decide what is better. So I want to show you two literature, or give you two literature advices here. The original image and painting paper by Bertalmio is really cool on image and painting. They tried to get rid of stuff over the photo with some first machine learning ideas. And just recently, from Ella Rus et al. On the right side, you have a kind of a review paper on image in painting and different machine learning techniques, so sequential-based, CNN-based, and GAN-based methods. It's really a huge overview with a lot of techniques out there. If you guys interested in that, there you probably find a method which could be interesting. So 2018, this YouTube video was coming out from NVIDIA, based on a paper on Liu et al. To image and painting for irregular holes using partial convolutions. So I will start now this video. Hopefully you can see that as well. Oh, we don't need the sound. So I was watching that video, but what you see basically is on the left side you have the original photo, and you are able to kind of delete stuff from the photo. And on the right side, the machine learning or AI algorithm tries to make a real picture out of it again without the missing values or the missing parts of that picture. So here now we get rid of the bridge and kind of it puts in the structure of the stones and so on. So I was pretty impressed by that video, because what it basically does is two things in our to translate into our climate world. It's kind of doing a linear interpolation in the color space. So it kind of looks at the picture and tries to kind of make a linear interpolation with stuff if it's kind of like just a white wall or here's some books. And so this part of the video is always a little bit longer, but it also can, what it can do is, if it's trained on patterns like faces, so it knows if you get rid of an eye, it puts back in an eye. So it's not just interpolating, it can learn on specific patterns and put them back in. And this was really interesting. Besides the facts, I put it on bold, the irregular holes. So in the past, a lot of techniques were using just squares or rectangles in the middle of the picture. But here it could be like, you could just, like paint, delete stuff on the fly and doing stuff. So and now this is a really cool example. This old white man gets beautier and beautier. With get rid of the wrinkles and so on and so on, and now it puts back an eye, deletes an eye, and it gets a female eye. And I love that the authors kept this example in, because this is another thing you always have to think about, especially in climate science. How do you train your data, right? You need to be careful that when you train your data, it must be clear that if you just train it with young female models, and you kind of try to do that on an old white man, then there will be a mixture, right? To think about the data, how you train it. So we come to that stuff, or to that point a little bit later again. So I was quite impressed by that. And when you go to the YouTube section of that video, you find some comments under it. And I found one really striking. So it was like saying, like, Google thinks, let's make AI that teaches itself to walk. Facebook says, let's make AI that develops their own language. And NVIDIA says, let's make healing brush tool from Photoshop. And a lot of people making fun under the video about it, that you get rid of some watermarks on that stuff. And I mean, it's a quite good joke. But however, there's a lot of potential. And I was thinking, could we use that for climate science? And I mean, a broken picture is never that broken, right? You saw the picture in the beginning with the women and this old photo. But here on the left side, pictures are never that broken. However, in climate science, we actually have that problem. So what you see now on the right side are it's an observational file, the annual mean of HZG and one really important climate data set, which goes back to 1850, which is a mixture of station, ship, and buoy-based data. And you see 2018 here. So this is the annual mean. So if there's a monthly missing data set point, then it gets a gray box. So this is 2018. If you go back to January 1850, the picture looks like this. You see a lot of land points are missing. You have some shipping routes there. We have these broken pictures actually in climate science. And I was asking myself, okay, can we do that? Could we like change the technology here? And this is how it all started. The video is called AI Reconstructs Photos with Realistic Results. That's why the title is Artificial Intelligence Reconstructs Missing Climate Information. And I done it together with the colleagues from NVIDIA, David and Uwe from Freie University in Berlin. And I will lead you a little bit through the results and how we get there in the paper. So I told you guys in the 2 slides ago that the training is really important. So you don't want to have female eyes on an old man, right? So the question was, how can we train the data sets without taking HZG4 itself? That was kind of the question here. So I thought about like maybe we could use our reanalysis data set. So and I took 20CR reanalysis from NOAA, which is basically an atmospheric model, which is driven on the boundaries with SST, so sea surface temperatures. And the beauty of it, it has 56 ensemble members. So it has a lot of data sets. So, right, from machine learning, we need a lot of training data sets. So I took these 92,000 month we get out of the 20CR reanalysis, which are basically images, if you want to translate it to the machine learning term. And then we took HZG4, so the data set we want to reconstruct in the end, and we took the missing value masks on it. So these are a monthly data set, so we have over 2,000 missing value masks. And then we threw that into the training, into the AI, and then we have a training set and a verification data set. I'm pretty sure you all guys know that. And to train the 20CR AI, and then having the 55th, so we used here just 55 ensemble members, and we left one ensemble member out, and this is kind of the 56th ensemble member, masked it with the original HZG4 missing value mask, and pumped it through 20CR AI, and got the result from the reconstruction there. So then you could argue, okay, the 56th ensemble member is pretty close to the rest, so I wouldn't be too impressed by that. So the second idea was, okay, let's do a second totally independent data set out of the historical experiments from the coupled model intercomparison project 5, which is from 1850 to 2005. So I took 35 models, and this they have different ensemble members. So was 145 ensemble members. So I took one out, and we have 144. This was nearly 270,000 months or images, and took again the missing value mask. Same thing here, doing the CMIP AI, have the masked one and reconstruct that one. This is already more far away. But what we could do now, and this was kind of the cool thing here, we could like reconstruct the CMIP one with the 20CR AI, and we could reconstruct the 20CR 56 ensemble member with the CMIP AI to have a cross-validation to make sure this is totally independent. We are able to reconstruct these things. And then, of course, in the end, we want to reconstruct HZG4 if kind of the evaluation works out with the other data sets to have the reconstructed HZG4 then. that was kind of the scheme. I know it's a lot, but that is kind of the transfer learning idea behind that paper. So if you guys have questions to that, just let me know. Okay, so the technique is written in PyTorch. It's used in partial convolutions. It's a CUDA-accelerated deep neural network. It uses partial convolutions. I think we discussed it in the seminar a lot. So it kind of convolutes down, gets the information. Basically, can say it's a classification task. So it can say if it's a dog or a cat. So I just wanted to say dog and cat here. So and it's a unit architecture. So it basically folds everything down and folds it up again because we want to have pictures in the end, right? Or climate data in that case. Okay, so put that aside. We put everything here now into that brain and keep it. I want to give you a short journey through the pre-research. Some people like it to see how it's done. So I find it pretty funny that it took me a day to find a computer with GPUs. I thought I had one, but it wasn't the case. So to find one to do that, to install the software which was applicable from NVIDIA, yeah, was really good. Then there was another one which was much more easy. You find the link in the paper. It took me 3 days, right? So to kind of download the pictures, so the MNet pictures and so on and so on. And then I wanted to run the software in its original mode to kind of put in real pictures and get some results. And that is something you see here. So that's kind of stuff, the image painting. Sorry. Oh, I know what you mean now, David was talking all the time. So that's a picture.
Gus, can I interrupt and ask a question?
Oh yeah, yes.
Maybe I'll give you a little bit of a break from talking.
That's great.
Can you before you go on further, these 2 data sets that you started working with that you used for the training and then the transfer learning, you had your CMIP5 and your 20CR. Can you talk a little bit about what kind of data and what kind of simulators are going into these data sets?
Yes. So the 20CR reanalysis data set is a numerical atmospheric model, which is forced by observed SST, so sea surface temperatures and sea level pressure information from the past. So it basically runs on the edges with information from the observation, and there the numerical model fills the gaps and does a reanalysis with it. So this is kind of an observational data set, but it's also not in a sense. But in climate science, we really love these things because you don't have any missing values. You don't have, you get results like precipitation, which is maybe not there on the observational files. So this is kind of a numerical model which is really close to the observations. And the CMIP5 historical experiment. These are Earth system models. So they usually are atmospheric ocean models combined with sometimes land and sea ice models. And so it's a big mixture of different numerical models here. And there you don't have any information of the observational past in there, besides greenhouse gas traces, so something like CO2 or volcanoes in the past. So you get kind of the climate trend correctly, and you get an estimate of the uncertainty of the past into the future, basically, kind of on 2005, the kind of the scenarios starts into the future. So these so this has basically nothing to do with the observational past besides the trend.
I see. That's quite okay. I see. So that's an important distinction for the 20CR. The data that's forcing it, the sea surface temperature data, is this at all similar to the HAD-CRUD4 data that you ultimately want to predict?
Yeah, it's not the same, but it's similar. Yeah. It uses basically the HAD SST data set, which is an already interpolated data set which uses kind of it's called head SST, which is part of headcrut as well on the sea surface side, but then it does some interpolation in space, so that the numerical model is not run on the sea surface side with missing values. So it's similar, but it's not the same.
And did you try this whole thing without transfer learning? Did you try only learning on the very limited HEADCRUD4 data?
Actually not, because you would like train that there is a missing value in a specific time, right? So the problem would be that the algorithm would learn that to a specific climate pattern there are missing values belonging to that climate pattern. But however, it could be like possible to kind of think about get the HEADCRUD data as well on board with these training data sets. But the problem of the missing value, so if you just think about photos, right? If they have missing values and your training data set have a lot of missing values, do you think it could like really learn that there's a missing value and you should, that's the reason why I never did that actually. If you think that would be possible, so what I can tell you what I did was like testing now as like filling the holes of HEADCRUD4 and then train it on that data set. That's kind of but I didn't train on the missing value data set.
Right.
Because the m-net data set is also not filled with holes, right?
Yeah. So maybe we can come back to this in discussion, but thanks. There's already a lot of useful information.
Yeah, that was helpful for me drinking a little bit. Thank you. Okay, so that was the result of the image in painting directly with photos from m-net. So you basically see on top a photo with missing values. You see the missing value mask beyond it. Then you see the reconstruction by the AI itself, then the reconstruction, the output composition. So every picture which is still evident in the first row is here as well, and then filled in with the AI. And on the bottom, you see the ground truth. I don't know how good you see that stuff, so I will go on here. So my first idea was like produce JPEGs. So I took my climate data sets and produced JPEGs with it, ran it through some NCL scripts, and kind of get these pictures. And I threw the JPEGs through the machine learning algorithm here, and that's what was coming out. So so you don't see it very good, but I was quite impressed that kind of the AI did quite a good job to fill these stuff in. However, you see on top of these, where's my mouse? Here it is. So you see on where you have a lot of missing values, you see some purple on the edges, and there I knew that the AI is cheating because of the resolution. So the data set is kind of 72 pixels, basically 72 pixels to 72 pixels, and the original software works with 256 pixels. So it was kind of cheating a little bit. So the big step was then change the AI software to read climate data and run and tune it and get climate data out. So this kind of took me 12 days or the most of the time, basically. So some technical fact sheet, if you're interested in that. So research applied at the Free University HPC and the DCAR infrastructure for the data handling. The AI models were trained using 500,000 iterations and 500,000 iterations for fine tuning. We used a batch size of 18 on a GeForce card. With 17 iterations per second, which was quite satisfying actually. But I guess could be faster as well.
Chris, so, what was the difference between regular iterations and fine-tuning iterations?
That's a good question. I couldn't. I knew that I could put it on, but I couldn't find really a difference actually in the software. But that's a really good question actually. As far as I understood it, is that it, no, I don't want to say something wrong now. So actually, I don't know. So it is, maybe it wasn't a big difference. However, in the original paper, they did it as well. So I thought it's maybe a good idea to do it as well. Maybe some of you could look into the code as well and tell me. Okay, so let's have a look at the results. So we have, let's say, a picture or a climate data picture. So this is now a picture, but however, I work with the netcdf file structure here, and let's put on a missing value mask of headcode 4. And then the picture looks like this. So what we see now is 20 CR, so from the reanalysis data set, a warm Pacific example, so kind of an El Nino case. And we put on the headcode 4 missing value mask, and then we use that as an input for the AI. And then the AI kind of puts out a picture. So there's nothing like a temporal evolution or something. It's just simple, a picture-to-picture reconstruction here. So and if you look at the structures, there are some really impressive ones, but not everything is perfect, right? If you look at some stuff here in the north, also the warming pattern here. However, the kind of the El Nino pattern looks quite good, even Australia. So I was quite satisfied with the first results there. So let's put on, that was kind of the reconstruction with the 20CR AI. So it is a 20CR data set, which is and then the AI is trained with kind of the data set. So the important question was, is the CMIP AI, so the one which is kind of trained with a completely independent data set, also able to kind of reconstruct that picture? And the picture actually looks pretty similar, not the same, but similar. That was really cool to see, actually, that it's the result is quite good, even if we have a lot of missing values here. So this is a warm example, and here you see a cold Pacific example. So you have here the original one on the right side, and even the structures here on the north. If you look at these things, I mean, this is quite impressive, actually. So that was really nice to see. However, if you look at Greenland, for example, you have a warming pattern here, right? You see the CMIP AI is not getting it, the 20CR AI. So if you go to the details, it could be also not perfect, and I don't say it is perfect. So and then I did the same thing with the CMIP data set, warm example Pacific and a cold Pacific example. And reconstructed it with the two AIs. Same thing here. Reconstructions look pretty good, but they're not the same. But of course, in climate science, we don't look at images and say they look good or don't look good. We kind of can do real evaluations here. So, and that's what was done and the next step. So what you see here is now the 20CR original one in black. That's kind of the global mean, the annual mean of the 56 20CR member, which was not part of the training. That's what you see now in black. If we mask that data set with the original headcode 4 mask data set, we get the dashed line here. And you see there are some potential biases coming with it if we mask that data set with the missing value masks. And now we can put in the reconstructed one from the 20CR AI and from the CMIP AI. And that was really nice to see. So not just on the grid space, but also kind of on the temporal space in the end. The two AIs are pretty similar to each other, and they're reducing the bias a lot. That was really nice to see. So this is kind of something we could do. So, and then we could look at some correlation and some root mean squared error here. So R and R minus E. So if we look at the correlation of the masked one against the original one, we have 0.97 correlation, so pretty high. That is due to the trend. And we have an error of 0.11 Kelvin or Celsius, degrees Celsius. And if we go to the 20CRAI and look at the correlations, it's much higher and the error is much lower, which was pretty nice to see. And we did some statistical testing there with bootstrapping to see if it's statistical significant. And that also worked out. Then, of course, as David already said, there are a lot of other methods out there, and in climate science, reconstructing these things is has a long history as well. And one recently very successful method was the kriging by Cotton and Way paper. They have the code online as well. So I downloaded the code and did the same thing with the data set here, so that you see now in gray. And basically, it also is much better than the masked version of the data set, and the error is also lower. We come to kriging. Kriging is pretty nice in kind of putting a signal into space. However, it doesn't learn anything. It has the potential to be putting a real signal into space, but it doesn't have the potential to find some signal which is not there. To find a signal which is not there, the PCA is kind of the EOF. Principal component analysis. So guys, the principal component analysis is a pretty long standard for reconstructing, for example, like linear patterns and so on. So, and there was also a cool paper by Beckers and Rickson in 2000. They found a method where they kind of iterate through the PCA process and to find signals. That is a strong competitor in climate science. So I put in this as well, and this is what you see now in Qian. I know the lines are maybe not so good to see, so let's have a look at the correlation and the root mean squared error. We see that the correlation is quite good, actually not as good as kriging, and the error is slightly higher than the kriging version. And this is something what, for example, Cottonway already mentioned, that there's always a chance to introduce biases if you use methods like these. And this is something which could have happened in our case as well. Let's have a look at a spatial reconstruction. Something we usually like to look at is some El Nino case, and I found a El Nino case which is really interesting, which was on between 1876 and 1878, so a very long and strong El Nino case. And so you kind of see a signal. You should see a signal of the in the Central Pacific during the whole year here. And the nice example here in July 1877 is that you see these shipping routes on the map, and there's a missing block directly over the Central Pacific, and you don't see any sign of an El Nino. So that was kind of a good task to test the method. And this is the reconstruction of the 20CRAI, which puts in a really nice signal close to, for example, Chile, where horrific rainfalls were detected in July 1877. So you see a clear warm pattern there, which could be El Nino induced. And by the other AI, we see that picture, which is not as strong, for example, on the coast to Chile. However, you kind of see still the signals of something in between the pixels which are still there. Of course, you could like compare that now with other methods. For example, kriging, the Coughton way, which was pretty good already on the reconstruction on the global mean and any mean we saw before. However, if you now put on a spatial map, for that example in July 1877, you basically don't see anything of a warm pattern over the Central Pacific, and that's just simply due to the fact that it's not meant to be like that. So you see now the effect pretty good that if you have a pixel, it puts kind of the information of the pixel into space until several thousand kilometers. So we wouldn't expect something like that. If you look at the PCA results, so the principal component analysis, we see actually something like a warm pattern, a slight warm pattern over the Central Pacific, which was pretty interesting to see actually that this is also kind of possible. However, it's not so strong, not so evident. So yeah, so it's not such a clear picture. I brought something with me today as well, because I put it just in because we had some really constructive reviewers, which said, oh yeah, what is really interesting is if you have an El Nino, usually you say El Nino is a little bit more on the equator, and your signal is pretty south. And yeah, that's probably true. And he said you guys should look at the new HZG data set, HZG4, which is not part of HEDCODE 4, and it will be part of HEDCODE 5, I guess. But they have new information, especially in the past. So I brought that with me now. So I made a mixture data set of HEDCODE 4 and HZG4. So basically, wherever HZG4 has an information which is not evident in HEDCODE 4, the information is now evident. And I know it's not much, but they found 3 more pixels, grid cells. So you see that in that yellow box. And what is really cool about that is it's a really strong signal in these 3 boxes they found. And that's kind of the region where the 20CR AI also puts on a strong signal. So that was I was pretty excited by the review command to check that. That was really cool. Okay, so of course, then we wanted to reconstruct HEDCODE 4. That was kind of the basic idea from the beginning on. So the observational data set reconstructed by the 2 trained AIs by these 2 different climate data sets. And this is what we have on HEDCODE 4 between 1815 and 2018. And you see a pretty good climate trend here. And if we put in now the 2 reconstructions by the machine learning or deep learning networks, first thing we see is they are quite similar again, which is a good sign. So so the whole cross validation idea worked pretty good here. We see especially differences in the early parts of that period. So I brought some trends with me. Oh yeah, I brought some trends with me. It's enough to kind of check the last column here. This is kind of the time of the trend which IPCC, so the kind of the last IPCC report used, and we get a higher trend by the 2 reconstructions here. And we have basically a cooler global mean temperature in the from 1815 to 1920 or something like that. So we basically get an underestimation of the global mean trend due to that due to the missing values. And this is something which was known before, so it basically says, yeah, it kind of confirms other studies. In the mid part, also it has a cooler period in the mid of the 20th centuries. There are other data sets out there like GIS and MLOST, which already said like probably headcrux is there a little bit too warm due to the missing values. And kind of the last part on the early 20th century, that was kind of the main focus area of that kriging technique, which checked if the hiatus phase, which was evident in the kind of 2000 to 2015, so 14, something like that, that we didn't have a strong climate trend. And they said kind of basically, you have missing data sets on the poles. So on the North Pole and South Pole, and there's something missing, and that's why you have kind of this hiatus phase. And yeah, in both areas agree on this weaker hiatus phase, so the trend is a little bit stronger there. And as well, the warmest year on record till now is 2016, and we see higher temperatures with the reconstructed one here. Yeah, so some nice climate science facts you could like study now with this data set. So the basic idea behind it was that we have HPC, high performance computing modeling, then we have this HPC processing, and we have these AI and machine learning on HPCs. That was kind of the idea here was to combine climate modeling with observations in AI. That worked pretty well. A lot of groups try to improve models with AI, so on different things. So here, kind of the idea is to have it vice versa, which was pretty nice. Missing values introduce structure biases, which can be reduced by the AI. Other studies are confirmed, but we see some added value and some combined signals, which look pretty good till now. I'm pretty sure the climate community will have a look at these data sets and will analyze them as hell. Yeah, the data and the technology will be continuously prepared for the community. So the code is on GitHub. It's not perfect yet. So it is the version I used for the paper. So we will work on that and we'll improve it in a way that the climate community can work with it. Yes, so kind of just a little advertisement here that we have now at the German Climate Computers Group Computing Center as well in AI research group. I'm really looking forward working with David and Marcel on these nice things. We have also the service part is increasing in AI. Tobias, I'm not sure if he's online yet. So we already discussed maybe using that technology and putting it out for the community. Maybe also there could be like a collaboration between the Helmholtz people and our group. So the summary basically is that we have the past, and the past is to a large extent uncharted. And we have this observational reconstructions from different groups out there, and now we kind of put in another competitor with machine learning, and it worked pretty well with the transfer learning idea to refill the climate information. Especially, it is kind of a mixture of interpolation plus pattern recognition, which work quite good. So as a classification tasks in ML. I just put on some thoughts, which I leave then open to be discussed. There's if you look at the review paper I showed before, there's a huge battle of the image painting community. So they get pictures and they want to be the best, and then they make a new paper and they say, oh, I'm better at this and this and this, so bring everything together. That's something I didn't want to do actually. So I didn't want to get all the AI methods and see what is best. So it's kind of the first step into that direction. And what I ask myself is, do they really care about a picture? I mean, we care about the climate information behind it, right? But do they really care about the picture? And couldn't we just, if they don't care about a picture, could we set up a climate benchmark out there and kind of say, guys, you use that stuff, maybe you could use climate data and make your competitions on that, to get a real cool method on our fee, on our questions, basically, because I'm pretty sure they don't care about the pictures. I know it's a little bit provocative, but can discuss on this. Speaking the same language is something which is always pretty important. As I said, the word ground truth is something in AI they use pretty often for the real picture. We had lots of discussions about the word ground truth, because nothing in climate science is basically a ground truth, not even an observational data set. And I discussed with the colleague who put out the code, actually, which I changed then. And he said, it's really cool what you do, but I don't get the climate stuff. And what, for example, is the difference between an analysis and a reanalysis? And that's a pretty decent question, actually. And that reminded me, oh yeah, we need to speak the same language here. Goes back to the first bullet point here. The world is on a square. We already had in that seminar the one on convolutions on the globe, and so what I tried to do with that paper was using the technology as it is, and being with the pre-research as close to headcrud 4 as possible, because in the end I wanted to reconstruct the headcrud 4 dataset. So, however, the pre-processing is not optimal on that sense, and the convolutions or boundaries are not a good idea. So we discussed that with Marcel and David already a lot. I just leave it open here. I didn't do any code optimization. So I used the technology as it is. I tried so hard to get it run, and when it was running, I used it as it is. So I guess there's a lot potential left on that. So on the optimization parameters and so on and so on. That's something we will look at. And if you guys are interested in that, yeah, please let me know. And I really hope that this technique gets beaten soon. That would be so cool. If the next group is coming saying, oh, that was a good start, but now we have a real competitor. Transfer learning needs science. That's kind of the putting a young female eye on an old white man. You need to understand what you're doing. That's the one we discussed with David, right? You cannot train on missing values, and but maybe you can, right? I mean, could be. I'm not sure, but that was kind of the idea, to have get a huge data set to train on and to bring the information to the AI, and then let the AI reconstruct the observations. Yeah, that's basically it. Thanks, guys. It's really weird to talk to just myself. I really hope we can do that in person at some point. I now see your point, David, and just talking into a empty room for an hour.
Yeah, it's difficult. It's
Thanks,
difficult.
guys.
You get used to it. You get used to the sound of your own voice at some point. Thank you so much, Chris. That was a fantastic presentation. I think we should always aspire to manage to cover this much material in such a short time. I think that was really great. I have lots of questions for sure, but let me open up the questions first of all to everyone else. If you want to type in the Zoom chat if you have a question, or if you want to type in the YouTube chat, we will have a look at that too.
So I see now you had a question in between.
Oh yeah. So let's see. I'm trying to remember what that was. I took some notes. Yeah, something I've noticed was sort of interesting. This may mean. Oh, you know what? Let's let someone else. So Eduardo, you want to ask your question? Or I can ask, because we just had a text in the chat. And the question is, what about reconstructing other variables from the available temperatures? Maybe pressure, maybe wind speed. Is this something that could be done?
That's an interesting question. So my question would go back to, if he means that we could reconstruct from the temperatures other variables without training on the other variable, or do you mean like, do we train other variables as well?
I meant, of course, training with other variables, but for instance, well, trying to reconstruct in the past, like wind, as you say, or sea level pressure, only from the temperature data that may be available in past periods. But of course, training with the variables available in recent periods.
Yeah. I'm pretty sure that works well on variables like sea level pressure. So like variables which are slow in time, which have connected information over space. I know everyone would like to see precipitation, and I also would like to do that. I'm pretty sure we could get it run. My idea now at the moment is to mix it up because, for example, the technology I use, which uses 3 channels, like RGB channels, and I use just one. So, and if we could like fill these different channels with temperature and precipitation and sea level pressure, then the AI would kind of learn an interconnection between the variables. That would be really cool. And I think this is something you could have in mind now, right? So learn something on the nowadays stuff for the past on other variables, but also learn other variables with temperature, because temperature has the longest record, right? With precipitation, we are not able to go as long into the past. That would be really cool, actually. So to combine different variables there. And then we could have a chance to have trained everything and just temperature and reconstruct as well the sea level pressure and the precipitation field.
Yeah, exactly. That was what I meant.
Yeah.
Could I pose a second question?
Sure.
It's related to the first one. I can imagine an application in paleoclimate. I mean, for deeper timescales, in which you don't have temperature observations, but just proxy records like tree rings and sediments, in which, well, they are distributed over the globe, and you may have in total, let's say, something like an irregular network of 100 records, let's say. So much less than you have for a hard crew case. Well, that would be also a cool application. I mean, there are many other statistical methods that have tried to reconstruct past temperatures, so over millennia. And if your method actually could be better, that would be a very, very cool application.
Yeah, I totally agree. I totally agree. That would be really nice. And I mean, you don't have to look on the globe, right? I mean, I did look on the whole globe because of Headcode 4. But for example, if you go to older, longer past, so timescales, I don't know, the millennium, last millennium or something like that, like the tree ring or corals, we could like zoom in, right? We could like zoom into Europe or whatever, where we have these things, or in the Northern Hemisphere. And we could like train on these millennium model runs we have, right? We have these Millennium run from Max Planck. We have the PI control runs from CMAP, and we have these very, very long runs we could like train the method on. So I think there's a big potential. And if you like to discuss with me about it, and you have some ideas, please let me know. Would be cool.
Sure. Yeah, I would be delighted to talk about it.
Yeah, cool.
So, any more questions? I let me ask a question while we wait if anyone else has one. So, Chris, you showed these 2 graphs of the mean temperature versus the estimated temperature with the AI methods. The first one was on 20 CR. And what I couldn't help but notice there is that all of the AI methods tend to make an estimate, which is just, okay, you can share my screen.
No, I just
Sure.
wanted to start the,
Oh, yeah.
you probably meant.
Yeah, this graph, the graph over time. I think you're slide 13. Yeah.
Yeah, this one.
Right. All of the AI methods make estimates of temperature, which are just a little bit too hot.
Mm-hmm.
Whereas when you look at the head data, the AIs are a little bit too cold.
Yeah.
Is there some explanation why this might be true?
Yeah, I think it's kind of, it learned the pattern which kind of are missing in that. So it reconstructs, it kind of reconstructs 1 month, right? So what we here have is a spatial and a temporal mean, right? Which comes into play here, and kind of it reconstructed on a month. So, and we see these effects. You probably mean something in here, right? So in the middle pass. So
Yeah.
so if we go here, so that it sometimes overshoots and undershoots, but it's more a cold bias, right?
Yeah, and
So
more of a hot bias than 20 CR.
No, it's actually not.
Compared to the original, the AI methods are lower than the original on, they're higher on 20 CR and they're lower on HeadCrit 4.
No, maybe it's confusing now with the lines, because in that graph, you see that, right? You see that now?
Yeah.
So the original one here is the real black line, and the dash one is the missing value one, right?
Yeah.
And the missing value one is kind of the original here. So it's kind of.
Oh, I see.
That's kind of with the original. So that, I know this is confusing. That's why I put the mask here as well in very big letters, because
Right,
so
that makes a lot of sense. So that explains the bias on HeadCrit 4. But what it doesn't explain to me is on 20 CR, if we look at the original, which is what it was trained on, it still tends to be too high rather than too low up until whatever 1950 when it gets everything right.
Yeah, there's definitely something missing, right? And there's still potential to be improved on this, on these missing values. But you have to think about how less data you have in this early period, right? I mean, there's the missing values are looking like this, right? I mean, this is kind of the picture you have, and there you do a field mean and an annual mean on that, right? I mean, that's kind of, that's something. There's definitely some information missing, and it's still not perfect. You're right. So if we look in that,
well, I think these results are great.
yeah,
and I
but
don't think,
still,
I'm not saying they're not good results. I'm just curious why the bias should be consistently in one direction. Maybe there's a physical explanation.
Oh yeah, it is because of the regions which are mainly missing. That's kind of, you could, like, if you kind of miss out a lot of the tropics, and the tropics are warm, and therefore kind of you get that bias in that direction, and that's something. It's pretty typical, and that's something with the later period here in that sense, where you have very less information's missing, but still kind of a lot, not compared to the early phase, but kind of for today, on the North and South Pole, right? So something like you see here, right? And these are the cold regions which are mainly missing. That's why this goes into this direction. It kind of depends on where on the globe you have the missing things. But that's an interesting research question, actually. Kind of, I use the real missing value mask. If we put on artificial missing value masks, which blank out specific regions, we could, like, now research how this is affecting the reconstruction of these methods, right? So this is something you point, that would be a valuable question here.
Yeah, I mean, this was also going to be my suggestion. If you did want to train on only HADCRIT4, you could do some additional masking, and maybe at random during training, and then you might not need these other. But I think you might still not have enough data.
Yeah, you
But
don't
this might be
have
one way to
data.
use only the HADCRIT4 to do the training.
Yeah, but then you have you get kind of a trend bias into it, right? So let's say you have a lot of missing values in the early phase and not many in the late phase. So you probably have a problem in the early phase there as well, to kind of train these things. So I'm not convinced yet to use just HADCRIT4 on that. Yeah. Yeah, I'm not sure actually if we put an hour, we could test it. I mean, that's not a hard task to do, but I'm not sure if that works.
So I'm going to see if we have any more questions. Nothing in YouTube.
If I could have a question quick. Regarding that figure 2 that you just showed. So if I understand it correctly, you're getting these time series of global average temperatures from a 2-stage process. First, you're filling in the maps spatially with the inpainting, and then you have a second process that then takes the average temperature
Exactly
over these maps. Did you try to compare with a method that eats an incomplete temperature map for a given month and doesn't map into the complete map for the same month, but directly into the temperature number? Because then you would expect that on average it shouldn't have a trend of underestimating the masked value, that dotted line, right?
Yeah, so you would like kind of train, so you would like put on the, let's say, the global mean temperature right away, you mean?
Yes, so I wouldn't use the ground truth full maps, but just compute the average temperature over the ground truth and use that as a target. So a regression from a full image just into a single number.
Yeah, I didn't check that. I know colleagues of ETH are doing something like that. So colleagues around Sebastian Zippel, they kind of try to kind of forecast the global mean temperature on a direct way. And you're right, that should be possible as well. But let's say vice versa. People weren't impressed about the global mean temperature time series. They were impressed about the spatial reconstruction, basically. That was kind of what the community really liked. The global mean temperature reconstruction, a lot of people are doing statistical stuff with it. I'm not sure if it would be a nice competitor. You're right. Yeah, I totally agree on that. But here, in that case, the people were mostly impressed about the spatial reconstruction, and then on the next step, doing an average mean on it to kind of compare it to the global mean time series. But yeah, you're right. It should be possible to kind of link the spatial information of the training just to the global mean. That would be a nice test case. And yeah, it could be that it already beats the one because it has less spatial uncertainty on it. Could be interesting test.
At the very least, you could subtract this bias from your map.
Yeah, you're right.
So there's a question from Lawrence on rainfall.
Yes, thanks. Hi, Christopher.
Hi.
I had a question a little bit in the same direction as Eduardo, but on a very different timescale. I mean, one of the big issues in rainfall observations is that the network is usually much less than, not dense enough to really track rainfall over days, for instance. So, and for some regions, we do have radar images for the recent past. And would it be possible to train network on these radar images and then use, for instance, the rain gauge stations, of which we only have few, which is more or less the ground truth, and then do a kind of backward reconstruction of past rainfall events. I'm really thinking about daily time steps almost. This would be for water management where I'm working in. This would be extremely useful, because usually this these statistics of these spatial events is often missing for many regions, not just in Europe.
So would it be like you have like a station information which goes long into the past, but you don't have a spatial information? So you would like train the spatial information next to the point information and then reconstruct it in a way that you have a spatial information again. So it is not really infilling, right? So it's
in a way it's infilling, because you do have point observations of the rainfall sum at a particular location, which you can relate to the image, which is the radar image.
Okay. I see. Now I get it. Yeah, I see it. So you have many stations.
The radar. I mean, in most places now, even in Africa and Asia, you have radar stations, but these were not there in the past. So you don't have the statistics, but you sometimes have rainfall stations that go back further in the past. And you could reconstruct it. I mean, it's much more patchy, I suppose, than a variable such as temperature. But
I think it should be possible. What I already started is testing on hourly data actually from ERA 5, so just to see if kind of this whole setup I use kind of breaks down, because it's just too much, and it pretty much worked. So so I don't see a point that. So daily scale shouldn't be a problem. And I like the idea of the radar data next to the rain gogs and kind of have a spatial picture there. And yeah, it always depends on how many stations are available, right? Even in the past. So you need some spatial information of these rain gogs. But I think it should be possible to train it on radar. It always comes with different weather situations, right? You have to capture a lot of weather situations with the rain gogs. And if you say like, we have like 10 years of radar data with basically all big events and kind of climatology weather on board, that would be a nice test, actually. I haven't thought about radar actually yet. That's pretty cool. I would have used ERA 5 or something, or the ERA 5 forecasts, precipitation fields or something like that. But I think it should be possible. And the same answer here with we could zoom in, right? It doesn't have to be a global picture, which would make the whole setup a little bit easier. In principle, I would say it's possible. Just always as precipitation answers, I guess it could be hard to get signals like a real precipitation field, but on a daily scale, so like daily sums or something like that, it should be possible. Same answer as Edo. If you have ideas to that and would like to discuss this, please let me know. If this would be an application which at Garrix could be used, I'd love to share ideas and give the technology out. Would be great.
Yeah, no, thanks. I will drop you an email. I have some ideas on possible data. So yeah.
Yeah, cool.
Okay. Thanks.
All right, so I don't know if we have any more questions. Let's check the YouTube chat one more time. I think that might be it. Yeah. All right, so thanks a lot again to Chris. That was a really interesting presentation. It's clear there's a lot of future potential for this technique. I think it's going to be really interesting to see how how it gets extended to different domains, how different architectures get used in the same task, and so we'll keep an eye on it. So thanks a lot, Chris.
Yeah, thank you guys. And if you have other questions or want to just write an email or something, please let me know. I love to discuss about that stuff, as you know, when I'm in the seminar as a guest. Please let me know if you want to call me or something and discuss stuff. I'd love to share my ideas on this, on your task.
That's great. And if anyone has a potential idea for the next session in 2 weeks, if they want to present something or just want to suggest something, please just drop us an email. And thanks to everyone.